Okay, so what did we talk about last time? Janet, what did we talk about last time? Normal distribution, excellent. So tell me about the normal distribution.
The bell curve.
Excellent. So that our normal distribution has a bell curve shape to it. That's absolutely right. And what else do you remember about it? Anyone? What else do you remember? Mm-hmm. Oh, yeah. Excellent. So what's the empirical rule?
68% are outside, or one standard deviation outside.
Mm-hmm. Mm-hmm.
Mm-hmm.
Exactly. Now, how many of you, be honest, how many of you memorized that? Basically, oh, wow. Oh, that's more than about 5, 6. That's a lot. But of course, you don't have to memorize it because I showed you how to derive it in Excel. How do we do that in Excel? So yeah, we can start with just the negative 1 and the positive 1 in Excel. And then there was some equation we put in. What was that?
Norm S.
Yeah, norm S. Yes, there it is. And we asked for the z-score, and that's something we'll be talking a little bit about today, what that z-score represents. But it's effectively just tagged to the standard normal. And then a comma to separate the argument, and then what did you type in? 1. Do you use 1 or true? I mean, it doesn't matter, but I'm curious which one you use. 1? One guys use 1? Not true. Right. I like 1 more too. I mean, I guess if you want to, you can just hit the tab button and put it in true for you, or you can hit it more. Let's phrase it right. Or if you want, you can select down and then it falls, and hit the tab button and select falls. But the selected one is faster, 0 is faster. And then we highlight this. No, press it over here. And in order to figure. And so what we did is we found this area. And we found this area, right? So how do we find just the area between the two? Exactly, we subtract the big one from the small one, and we got 68%. And what's also neat too, if you change that 1 to a 0, that positive 1 to a 0, that means you're getting this area right here, the smaller one. What should it equal? What should this one be? Just the one with the vertical. We'll make it a spot. We'll make it a pattern like this, flat pattern. What should this part be? 34. So did you do that? How did you figure that out? Did you just put in the 0 and make it put the 0 for the 1?
Well, 152 standard deviation, 68 for 1.
That makes sense, right? If this, as you point out, if this is 68, half of that must be 34. I know we can do the same thing too if we put in, this is 1, and this is 0, we get 34 again. So it's kind of fun, and of course now we just set this up, and now you can derive the other ones. There's a positive, there's 95%, there's a negative 3, and a positive 3, and there's, of course, the decimal point. 97, 99%. Now you can derive the whole thing. And what's even more fun is that you can do it for the individual. Oh, I want to know what it is between that. That's 84% between one standard deviation above and 3 standard deviations below. Okay, so you can have lots of fun. Any questions? This right here? So I'm going to have to change that to negative 1 and negative 1. I'm not sure that's a 0, but it's because of I.
I was just trying to figure you got 30. I know it's bad.
Yeah. Any questions on that?
So, what we were doing is we were putting this value in, and Excel spat out this area, right? Area because we set in a cumulative function to make the area underneath the curve, you have to take the integral. But I'm curious about going the opposite way. I want to know what happens if we say we know what this is. What's the value that gives us this result? To go the opposite, to do the inverse.
Well, that's what I'm wondering. Well, in order to illustrate how to do that, let's start with what would be practical about it. Why would you ever want to do that? Weird. So there's a lot of interesting applications, and let's start with warranties. What is a warranty? Oh, I don't know. Is Sebastian here? Okay. Yeah, I know this here. What's a warranty? Are you familiar with the term? Am I pronouncing your name on it? John?
No.
Hmm?
No.
None?
Yeah.
Okay, I had this on, sorry. No. What is a warranty? Anyone familiar with the term? I want to say it's Marie?
Yeah.
No. Okay. What's your name again? Anisha. Alright, totally wrong. Alright. How did I know? This is a boy, so get it wrong. Anisha, what's the warranty?
It's like let's say you buy like a phone
Mm-hmm.
and whatever happens if you drop it and it breaks or stops working or whatever, so you can take it back to the place that you bought it from, they'll fix it over with the warranty.
Exactly. You get a new phone, right? If it breaks, presumably they won't replace it if you like throw it against the wall and stomp on it. Though I don't know many people who would do that. But you know, if it just breaks, there's certain things that are covered, certain things that are not. Why would they do that? That's so nice. Why would they do that? This is terrible. From a business perspective, why not just say no warranties, and that we have to buy a new one? Ha ha ha! We get more money. Why replace it? Well, we'll talk a little bit about that when we do probability. But there's you're talking about extended warranties. I'm talking about just the standard warranty. So the one that, why do they give any standard warranty at all? Ike.
To encourage people to buy expensive stuff.
Oh, okay, great, right? So that makes sense, right? It's a selling point. So then why? So the warranty should never run out, right? Warranty should always last forever.
Although, I mean, the purpose of it, like the product,
Uh-huh.
and then there's something else that's up, like Apple, and then that's what I know.
So they're trying to hook you.
Yeah.
That's so mean.
It's cheaper to keep a client than to
Well, that's true. But, you know, you would get a lot more clients if you had warranties last forever, right? Because that's if some warranty is somewhat of a selling point, and a long warranty is a big selling point.
Well, that's why there's extended warranties, I guess.
Yeah, but you could but not everyone gets them, right? So So why does not everyone just have an infinite warranty?
Well, there's two, some people that buy it just because they know they know that they're more likely to break their phone or whatever it is that they're buying compared to others.
Mm-hmm.
But I think some companies do offer a limited time warranty with their products, or their electric house and that probably because they don't want their product to break and then have customers not have customers like go to another company to buy it.
Oh yeah, so it's a legitimacy issue, right?
Yeah.
But what I'm saying is, if a 1-year warranty is a selling point, and let's set aside the issue of extended warranty because that's a whole other thing we'll talk about later. But if a 1-year warranty is a selling point, then a 2-year warranty should be a stronger selling point, right? So
But there's always new products coming out too, so some of the cars will stop being made.
That's-
Some cars,
that's true.
you know, so what's the point of having a lifetime warranty if some cars are not no longer like the car never says no longer exist?
Yeah, let's imagine that a company had a lifetime warranty. You bring up a really good point. If they had a lifetime warranty, what would be the problem from the company's perspective?
What would be the problem?
Yeah.
That they can no longer create new products like with new pieces because the old pieces have to be made.
Yeah, and it's just expensive too, right? Like, if it's harder to get the replacement parts, then that's more expensive, and they have to maintain. They have to essentially compete against themselves, as you point out, right? It's like we have to replace the one that we made, and if it literally lasts like 20 years, not only is it expensive from the perspective that we're competing against ourselves, it's also expensive from the perspective of we have to keep buying people new shit, right? So.
Is it also because like they're with 1 year because they know that like if you cancel like something or anything happening to your product in the first year is very low compared to
So like
Yeah, and I mean, obviously, it's more likely that you will have something happen in the first 2 years than something happen in the first year because 2 years is longer than 1 year. But I think what you're saying too is more than that. Like the first year, people take super good care, and then the second year, they're like used to it and like whatever, right? I don't care anymore. And that's part of the story. But and that relates to what we're talking about. It's also like one of the things that they care about because some things they don't cover in warranty, some things they do. Like if for some reason your hard drive fails too, that's covered in warranty, and that's not necessarily something you did to the thing. That's not a care issue. That could be faulty manufacturing in some way. So they recognize that there's going to be a distribution of performance that they can't control. Some things by random chance because of the quality of how that particular unit was assembled or the components were assembled might be higher. Maybe someone else, maybe the assembler was sick that day or wasn't really paying attention and didn't do as good of a job. Or maybe the quality of metal is different, or maybe the assembly of some part is different. So, for reasons that the company cannot control, they recognize that sometimes the quality is good and sometimes the quality is bad. So, how do they figure out 1 year and not 2 years, or half a year, or 8 years? Because sometimes you see like 8-year warranties, sometimes you see lifetime warranties. It's rare, but sometimes you see it. And one way we can do that, oh yeah, Adam, you want to jump in?
I was going to answer your question. I feel like they're kind of like looking at it like, you know, they look at all the possible scenarios that could have happened, that they could have messed up on.
Mm-hmm.
And they say, okay, well, you know, if we messed up on A, B, or C, it would have to show up within 8 years. And if it doesn't show up within 8 years, then we could have made a mistake because it wouldn't have lasted.
That's true, right?
So obviously,
So yeah, they could look at some
engineering into that.
Yeah, it sounds like a calculation sometimes. I bet they have a lot of data on how long stuff typically works. They can do product testing all the time, right? So let's imagine, because again, this distribution comes up a lot, so it's not unreasonable to say this. Let's imagine that phones last, the performance of phones follows a normal distribution. That a few phones really will screw up super fast. There's an average length And a few phones will last super long time. Sometimes due to care that the customer gives, but sometimes due to the inherent quality of that particular phone that was assembled. It's slightly different than the other ones. And sometimes too, it could be based on weather. Like maybe phones in Florida last less long than phones in Boston, because phones in Florida are more exposed to heat, and that's not necessarily good for electronics. So let's imagine that we're trying to figure out the optimal warranty length. Recognizing that it follows a normal distribution. Let's say phones last, how long do you think an average phone lasts?
2 or 3 years.
2 or 3 years. Keep in mind, oh yeah, well, that's all right. Yeah. Let's say 3 years. Now let's give a standard deviation of, I don't know, 6 months. Yeah, let's do 6 months. How would I express that here? I'm going to put in 6. 0.5, right? Because this is in years, so this should be in years too. If you put in 6, that means you're saying 6 years, and we don't want that. We want half a year, 1.5. Now let's imagine that the company accountants figure out what % of phones they can replace and still turn a profit. So what's an acceptable level? And we can't replace any more than this %. And let's imagine that they determine we can replace, I don't know, 6% of phones. Admittedly, these numbers I literally just made up now. It might not turn out exactly how I want, but it'll be close enough. So we have now a situation that's exactly the opposite of what we did before. Before, we put in this number and we want to know what the area was. Now, we know what the area is, 6% on the curve, and we want to know what number will give us that area. So we are going to use the command norm.inv. And it asks for 3 different inputs: probability, mean, and standard deviation. What should we put in for probability? I think I heard it. So we should put in 6% or 0.06 exactly. We don't want to put in 6 because again, this is going to be bound between 0 and 1, and we're going to put in 0.06. Or 0.06 if you want. I always like to put the 0 in front of the decimal point. It's just a good way to make sure you don't miss the decimal point visually. So it's a good habit. At least I think it's a good habit. I do it. What's our mean? 3, right? The last average of 3 years. What's our standard deviation? 0.5 or 0.5. Again, I don't care what it is. I'm just using the 0 from this. And we get 2.22 years. In other words, 2.222,613. This gives us exactly 6%. I have to add some more stuff here, but this will give us 6%. So, the accountants say we can replace 6% of phones. How long does their warranty last? And you pull up Excel and say it's going to last 2.222,613 years. Roughly. We're good so far? Okay, now let's find out what's wrong with that. From a branding perspective. It's not a round number. What's the warranty? Well, it says 2.222,613. What? So, yeah, you're right. It's not a round number. We should make it a round number. What should we do?
2 round down.
We should. So let's round down. Now, if we round down, does this number go to the left or go to the right? It goes to the left. Right, absolutely. It's going to be farther away from the 3. Does that result in 6% anymore?
No.
No. Does it result in less than 6% or more than 6%?
less. So in this case, that's fine, right? We can afford to replace 6%. We're going to make it 2 years. So we'll be replacing fewer than 6% of homes. And that's fine from a company standpoint. But let's imagine, just for simplicity,
Let's imagine that wasn't 2.22216. Let's imagine that was
1.9, hypothetically. If it was 1.9, and we rounded up to 2, what would happen to that 6%? Would it still be 6%? It would be more or less. It would be more, right? Because we're going this way now, and we're going to expand that area. We can't afford to replace more than 6%. We can only do 6 if you round it up in this particular case. Then you're going to put the company into homes. You're going to be replacing more than 6% of homes. That's not something you want to do. So if this was the answer, you might be like, maybe do an 18-month one. 18 months, a year and a half, and you say a year and a half, that sounds weird. 18 months doesn't sound that weird. Right? Or if you really want to be conservative, just make it 1 year. Right? But again, 18 months doesn't sound crazy. Right? So
You have to think about these things, right? This is not, I mentioned this is not the end of the story, just put it into Excel, because again, you're going to have a step of actually translating to something customers will accept. And it gives you something to work with. It gives you a starting point.
Let's see if
Of course. Expand a little bit. Any questions? 0.06 came from we're replacing 6% of phones.
that's the area.
Yep, that gives us the area under the curve.
You know that we can also put it in the calculator as well? Because when I was doing the simulation,
Oh, interesting. I mean, we're working with Excel, so because Excel has all this built in. And the problem from a assessment standpoint is that those kind of calculators can also store things that you shouldn't have access to, like, notes or so forth. So, yeah, I typically don't allow them. So, let's do another one. Let's imagine that you want to give people a bonus, right? You work in sales, you're a boss of a lot of sales individuals, and you know that on average, people, I think I use 40,000 notes. I'm going to use 400,000 because 400,000 kind of makes more sense. That the average salesperson brings in $400,000 in sales every year. And let's imagine the standard deviation of that is $50,000. And you're like, I want to, those people that do really well, I want to give them a bonus. I'm going to give a bonus to the best performing 20% of people. So what should my cutoff point be? Maybe you make an announcement to you and you say, look, if you make above this amount of money, I will give you a bonus.
How would we do that in Excel? How do we figure out what our cutoff point should be? Take me through it. All right, here's your hand. We start with normal number. Yeah, CJ.
So probably 1 minus 2.
So we also do it right. So sometimes, for those of you who don't know what we're talking about, we're going to do it the roll-up way first, and then CJ will tell us why it's wrong. So let's do it the wrong way. So you blindly look at this and you're like, oh, bonus is 20%. Well, 20% is 0.2. And then we're going to do 400,000. And then we're going to do 50,000. And then we'll put it in. And here we go. Okay, so let me add a comment here so you can see it. Oops. There we go. Okay, so that's what it should be. It should be 357,918. That's the starting point. Right? Now, what did I do wrong, TJ? What's wrong about this?
Yeah, 20%.
I'm at the bottom 20%, right?
I'm now rewarding the top 20% of people. I'm rewarding the top, what? 80% of people. All right? Because again, Excel always looks at the value and lower. I found this, but I don't want to find that. I want to find this. I want to know what that number is. Because these people are the 20%. These are the folks that get 80. They get nothing.
And you should immediately know too, this is odd because my cutoff point is lower than my average. So that seems like a pretty simple hurdle to jump over. So why is it that I make it 0.8 CJ?
Because since you're at the top of the percentage, you see that it is the birds.
Mm-hmm.
So since you're trying to get you minus 0.2.
Mm-hmm. Exactly, right? Because I want to find the cutoff point for the bottom 80%.
And I'll use the top one for the top 20%. And now, oh, that makes more sense. $442,081.06. Are we good so far?
So, at the weekly meeting we have for my sales team, I'm like, okay, folks, look, so if you get at least $482,081.06 in sales this month, this year, we'll say it's this year, I'll give you a bonus. I'll give you like, I don't know, $10,000 bonus or something. What are you thinking as a salesperson?
It's not a wrong number.
Yeah, that's like weird, right? Sort of gravity fall. So what should we do? Should we round it to 400,000 or should we round it to say 450,000? Why?
Because you're going at more 20%.
Mm-hmm. Exactly. So now, before we wanted to round down, this one we want to round up because we want to get farther from the center point. So we don't want to make these tails too large. So we're going to maybe make that, 450,000.
And as a side note, if you're curious, okay, what percent am I actually reporting? What percent am I going to be getting to? Well, 450, 123. Nope, I don't want to know. If you put in a comment, then it thinks it's a different argument. Mean is 50, then I comma 1, and then you do 1 minus that. It's about 16%. But we're running 20% or 16%, that's not really bad. Granted, we can fiddle with this like you would say, and any economist worth their salt would say, well, if that's the case, if you're giving a reward for really high sales, you'll get higher sales, right? And in some way that the normal distribution doesn't apply anymore. Not like that's true, it doesn't. But at some level too, that's kind of okay, because if I get more sales, I can also afford to give out more bonuses. I might, based on these incentives, be giving it out to, even though I signed up for it's only 16%, I might be actually giving it to like 30%. But I'm not able to afford that because I have more sales. So change those incentives. Again, it gives you something to work with. Because if you're really concerned, we can then drop down even more than 50,000. Probably not off there, drop. I don't know. Alright. Are there any questions on this? Yeah,
Yeah, why do you subtract
Oh, because when I did this, I found this area, but I really wanted to find this area. So 1 minus it. Any other questions? All right, precious little time to do the next part.
We're going to switch over now to confidence intervals. I'm going to give you a little primer on it. We'll be talking more about it in next class anyway, so obviously we won't finish with it tonight. But I want to at least get to the equation part.
A sample mean
Is by definition our very best guess at the population.
assuming that the sample was, there's no bias in the sample, it is our very best guess. It is what we call the point estimate. But we recognize as well that no sample is perfectly precise.
Why do we say that, Jamie?
Because you can't take a precise sample. It's impossible to take a precise sample of a population.
Why?
Because there's always, well, there could be bias that exists, or,
Well, we kind of said there's no bias. No.
like, there's random sample. When you sample random, there could be people who are represented and others who aren't.
Yeah, just for random chance.
Exactly. Not because they did anything wrong, just because by the central limit theorem, we recognize that sometimes samples are just weird, right, by random chance. So, because those samples, though, follow a normal distribution, those sample means follow a normal distribution, we can estimate how likely is it that we've captured the true population mean. That we take a sample, it might be a little higher, it might be a little lower. How likely is it that we've captured the true population? What's the range, we should say, that we've captured the true population mean? And that's a confidence interval. Confidence intervals are defined by a couple of things.
Chiefly they're defined by their confidence level.
Which is the chance, the confidence interval, includes the true population mean. If you've ever heard phrases like 90% confidence, or 99% confidence, or 95% confidence, that's what this is a reference to. Here's an interval. There's a 95% chance that the true population mean lies in this interval. If we were to take 100 sample means, if we were to do this experiment 100 times, 95 of them would be in this interval and 5 would just be weird. Maybe those 5 are right. Maybe one of those 5 is correct. Right? So again, it's not perfectly precise. Maybe these other ones were weird. Right? But there's a 95% chance that it's in this range, or a 99% chance, or a 90% chance. You've seen these too. You've seen these when, like, they say, "Oh, we did a survey and 80% of people like candy, plus or minus 5%." And if they're really good, they'll say, "That, by the way, is at 99% confidence." You ever see that plus or minus 5% before? They do it a lot, like fold in and say plus or minus 3%, plus or minus 3%. You ever see that before? That's what this is a reference to. They're making a confidence interval. This area right here, this number is what we call the margin of error.
It is the value that you add and subtract from the average to get that range.
Add to, I guess, and subtract from. To get your confidence interval.
This is our confidence level right here, and this is our point estimate right here. So, in this example, there's a 99% chance that 75 to 85% of people like me. Yeah.
Does that mean as the margin of error drops, that the confidence level also drops?
Well, see, if the margin of error, let's see, the margin of error drops, that means this is smaller. So it's a narrow range, and then the confidence level drops. Yes. Because you would expect if it's a 95%, if it's a 99%, 99.9%,
You should expect a really big range, right?
Yeah.
So you're more likely to capture it. And if it's 90%, then it only needs a small range. Exactly right.
Any questions so far? So,
Let's get some definitions. Let's get some common confidence levels. They are 90%, 95%, 99%, and 99.9%. Those are our standard confidence levels we use a lot. There is a analog sort of description of the confidence levels. There's another way to put it, and it's called alpha.
alpha is sort of the opposite of it. In fact, I mentioned alpha to you because Excel often likes you to put it in the alpha level. They don't like putting it in confidence levels. But they're equivalent, they're just mathematically different. But they're,
They just essentially describe the same thing. Confidence level is the chance that you captured the true population mean. Alpha is the chance you didn't capture it. You did not capture it. Capture. And unlike confidence level, this is always ranged from 0 to 1.
So confidence levels are always percents, alphas are always max at 1, minimum 0. We want to talk about alpha a lot. In fact, alpha has applications beyond our confidence levels. So don't get too hung up on this literal definition that it has to be within an interval. Alpha has a more technical definition, which we'll talk about later. I don't want to get into it now. But for our purposes right now, today, you can think of alpha as a chance that we missed. Alpha is the likelihood in a 0 to 1 scale that it's outside this range we've established.
And you can just mathematically determine it really easily. If this is a 90% chance that we got this range, what's the chance that we did not get this range? Well, what's the chance that the true population mean is not in this range? If it's a 90% chance it is, it's a 10% chance it's not. But alpha is always described between 0 and 1, so 10% chance is 0.1. 95% chance is translated into 0.05, right? 0.05. 95, that's 0.95, it's 0.05. 99% becomes 0.01, and 99.9% becomes 0.001. Any questions so far? Great. So now we're going to take this alpha, and we're going to recognize that two possible things could happen if we're wrong. What are the two possible things? What are the two possible things that could happen in this range of 75 to 85%?
It could be too high.
Exactly. It could be too high. It could be too low. I'm trying to do it from your perspective. So this would be too high. This would be too low. In other words, you can take that percent chance, that let's say this 0.1%, this 10% chance, and you can put a 5% chance over on this side. There's a 5% chance it's too low. There's a 5% chance it's too high. Okay? There's no reason to think that one is more likely than the other. The normal distribution is symmetric. So in order to essentially do the math, we have to be familiar with a z-score. And the z-score is going to have a subscript to it, alpha divided by 2. In other words, it's what we'll call a two-tailed test. It's another way of saying, look, we're recognizing that things can either be too low or it can be too high. And each one of these confidence levels has a particular z-score associated with it, hardwired into the system. Will you have to memorize these z-scores? No, never. If you do a lot of statistics where you end up kind of memorizing some of them, yeah, because you use them a lot. I can never remember now. It's 2.576. I want to say, is that right? Yeah. And this is 3.291. I believe for 99.9. Yep. If you were to do these calculations by hand, which you probably should know how to do, these are the numbers you use. If you use Excel, Excel will ask you for an alpha score. So Excel has this built into it. But I should still show you it. Because it's helpful to know the equation for something we'll cover later. So here's our equation. The equation for confidence interval of x bar equals x bar. So that's our point estimate. And then the next part is going to be a margin of error, which means we're going to be adding the margin of error and we're going to be subtracting the margin of error from this value. And that equation equals z, those are alpha divided by 2, sigma, square root of n. Take a moment and appreciate the logic of the equation. If we have a larger n, if we have more observations, we know more about what's going on, right? The likelihood that we got something unusual should fall. Sample size of 5 is not as precise as a sample size of 50. So as n increases, what happens to this value right here? If n increases, this gets smaller. If this gets smaller, what happens to the margin of error? And this, by the way, this part after the plus or minus is our margin of error. Margin of error. What happens to the margin of error if this gets, if n increases, this gets smaller? So what happens to the margin of error? It gets smaller. And so in other words, we get a narrower range. That's good, right? A 99% with a huge range is not as good as a 99% with a small range.
You might think 99% or higher confidence levels are always better, but higher confidence levels have a cost to them. They make the range larger. Is it useful to say, we'll get anywhere between 0 and 500 inches of rain tomorrow? Right? Is that useful? No. But is it really unlikely that's wrong? Yeah, it's like 100%. I mean, you might get 501. I don't know. Weird things happen in the world. I don't know. Right? So a larger range, a larger confidence level is nice, but a smaller range is also nice. You kind of want both. And if you increase n, you get a smaller range holding everything else equal. That's good. Appreciate too, though, if we note that the dispersion of the data naturally changes a lot, right? It could be over here, it could be over here. Then, if this increases, we have to cast a wider net to be able to confidently say that we've captured the true population mean, holding confidence level constant. Yeah.
So the mean plus or minus margin of error gives us the confidence.
So, yep. We should have two numbers, a lower bound and an upper bound. Z-score. As the confidence level increases or as alpha falls, what happens to the Z-score? Exactly. The Z-score increases. So therefore, the confidence level, the margin of error increases, and the confidence level gets wider. If this was, say, 90% confidence, we would only have to cast a pretty narrow net. Be able to say, oh, with 90% chance we captured the true population. This might only be like plus or minus 3. If we want to say 99.9% confidence, we would have to cast a larger net. Would have to go from plus or 2.576 to 3.291. It has to be a little bit larger for us to capture that true population mean. Be able to claim that with 99.9% accuracy. So there is a trade-off. Like so many interesting things, there is a trade-off. Any questions? So I've been focusing on this percent, like these plus or minus 5%, and this equation doesn't really describe how to, I mean, it thematically captures it, but it's technically not the equation used to capture a proportion. So there's going to be a separate equation for this, and there's a different equation for proportion. I'm also assuming something here that's a bit, unusual. I'm assuming I know the population standard deviation. I assume I know sigma. You don't necessarily know sigma. And so these kind of complexities are something that we're going to be talking about in next class, and I'll also show you how to do it in Excel. So we're going to have a busy next class, but right now I'm out of time. And so I will see you on Tuesday. Have a great weekend, everyone.